So first I would like to thank the organizer for giving me the opportunity to discuss a solution, this BeeGFS solution we recently adopted at the Geneva Observatory. So in this talk, I will first, in few slides, present you the Geneva Observatory. I'm sure there are some of you that's never heard about it. I will then describe what is this BeeGFS file system, and then I will also describe in more detailed way how we built this system at the Geneva Observatory. And I will end this talk with some simple benchmark we recently done. Okay, let me first introduce what is the Geneva Observatory. So it's an institute which is dedicated to the study of astrophysics and astronomy near Geneva. So it's split into two parts. One part belongs to the University of Geneva, Université de Genève. It has about 130 collaborators. And there is another part that belongs to EPFL, to more precisely the Laboratory of Astrophysics, and there are something like 40 collaborators. So this gives you a bit the framework. Geneva Observatory is situated between Geneva and Nyon, near a little city which is called Versoix, about 5 kilometers. It's hidden a little bit in the wood of Versoix, so it's not always easy to find it. Anyway, so the field of research that are covered by the Geneva Observatory are may be split in four different parts. So people try to understand how stars evolve, how they form, that's stellar physics, galaxy and cosmology. We have people that are interested in the formation and evolution of galaxies and how they connect, what we can learn from them in terms of cosmological models. There are people interested in high energy astrophysics. This is processes that involve high energy that we can find around black holes, neutron star, white dwarf, quasars, and so on and so forth. And finally, there is an important group searching for extrasolar planets. It's important to emphasize that the Geneva Observatory is tightly connected to several important European Space Agency space missions, and you have some of them here. For example, we are working in tight connection with the Integral satellite since more than 10 years now. Integral is specialized in the observation of high energy photons, so X-ray, gamma rays. Euclid is a mission that will be launched. We expect it to be launched in 2021, and we'll be able to survey a large fraction of the sky at a resolution nearly similar to the Hubble Space Telescope. Gaia is an operating mission which has been launched 5 years ago and did a very fantastic survey of stars of the Milky Way. And finally, CHEOPS is a mission that could be launched in few months, dedicated to the research of planets. I wanted to show you also very quickly this movie that show that we not only observe at the Geneva Observatory, or we don't only collect data, but we are also simulating astrophysical objects. You have here simulations that show the formation of dwarf galaxy in a cosmological framework, where you see here the red part is according to the accepted cosmology is dark matter, and inside this dark matter you form tiny objects like dwarf galaxy here. Okay. So in order to support the research performed at the Geneva Observatory, so both the research and data coming from space mission, we have a data center, rather modest data center, which have a capacity of something like 160 kilowatts. We have now something like 1,500 core, which are dedicated both to simulations, data reductions. And we are a team of 6 people dealing with all IT infrastructure, so not only dedicated to the management of this data center. Okay, so now let's move to the description of our new HPC storage system. I would like first to give you a list of constraints that helped us to design our HPC system. The first thing, of course, is that we would like to have a real HPC file system, so which support concurrent access. So we wanted to run parallelized code, so with plenty of tasks, and let the possibility of all these tasks to write into one single file. For example, like using typically MPI-IO library or HDF5. Then this HPC file system should be accessed by our cluster, so about 1,500 cores, and we expect to increase the number of cores up to 5,000 in 2022. Now, concerning the capacity and extensibility, so our actual needs are around 1 petabyte, but again, we expect to increase this capacity to 6 petabyte in 2022. So we really need a storage system that is easily extensible. Finally, we need also it to be versatile. As I just described, we need an efficient HPC storage, but we also need we expect it to use also it as a long-term storage. And this for several reasons. It's, of course, as you all know, it's not easy to move data from one storage system to another one. And the second point is that we have some applications that have quite important data, so several hundred of terabytes that need to be regularly processed. So there is no way to move those data to another system and move them back again. And finally, so the file system should support a large variety of applications which deal with different kind of files. About data integrity, so of course we would like, as we expect to use this data as a long-term, this data file system as a long-term storage system within some data redundancy. However, we don't ask for a snapshot. So this data file will be accessed mainly by code, so there will be few humans that will directly touch the system, so we don't think it's useful to have a snapshot there. Concerning the price, of course, we need it to be as low as possible. And wanted also to emphasize that we don't need, we have no need for object-based storage or a storage system with high availability. In fact, if something breaks down at the Geneva Observatory, I mean, if we need one day to recover the file system, that's not really an issue for the users, which is very convenient. Okay, so if you look at the available file system that you find in the market, I think when speaking about HPC storage, as we heard before, the first that came in mind is GPFS. So we had some experiences with GPFS, but for us, unfortunately, this solution is definitely simply too expensive. There are other solutions like Panasas, which has some drawback, like being also quite expensive and being hardware dependent, for example. Lustre, we heard about it just before. That's probably a very interesting file system, but for us, I mean, it's certainly too complex, simply. So we didn't try to use it. We had some experiences with not a very well-known file system, which is called BeeGFS, or parallel virtual file systems. But the experiences were not conclusive. It was quite complex to install and not very easy to manage. And finally, we saw appearing on the market these BeeGFS file systems, which seems to be really nice. So let's try it. So BeeGFS is really a truly parallel cluster file system. It offers a common storage speed, which is definitely spread over several servers. This project started more than 15 years ago. In 2005, it was initially called the FHGFS file system because it was developed by the Fraunhofer Center for High Performance Computing. Now it is supported by a private company, which is called ThinkPark, which offers support and consulting. But of course, you have to pay for it. I think there are many advantages for using a BeeGFS file system. Of course, it is supported on a Linux system. That's fine for us. We are running CentOS now. It is hardware independent, so this gives us a lot of freedom on choosing the servers. It is definitely very, very easy to install. So under CentOS, you have simply RPMs that you can very easily deploy. And there are few configuration files to touch. So if you have some experience, I think in one day you could easily deploy it. It is also very easy to manage. There are a few commands that let you deal with registering a new server or checking the data and so on and so forth, changing some parameters. It's very easy to extend. If you want to extend the disk, you can simply add a new data server. It will automatically register, and you're done. It offers data redundancy options. I will discuss this point later. Well, it also supports different network types, like the classical TCP/IP network, but it also supports random memory accessed network like InfiniBand or the emerging OmniPath. That's good. And finally, it's really cheap, as it is distributed free of charge under some licenses. OK, let me go into more details and describe how the BeeGFS file system works. So it's mainly based on 4 services. You have first the management service, which is responsible of registering any new other services and check that which services are available simply. So this is something I won't discuss in more detail. This is just a very light daemon that you can install on any kind of machine. Then you have, of course, the clients. So mainly, well, usually install on computing node that simply let you have an access to the data. And then you have the metadata service, of course, that knows everything about where are the data, what is the ownership of the data, what are the size of the data, how they are distributed along the data storage service. And you have the storage services that definitely, well, that really have store the data. So to better understand how this works, imagine that you are a task on a client machine, and you want to write a file. So the first thing you have to do, you have to contact the metadata service and saying, OK, I want to save this file. The metadata service knows exactly about all the data where they are stored. So the service will tell you exactly where you have to store the data, but it will also tell you in which pieces you have to split the file. So every file, before being stored in the data servers, has to be split in small pieces called chunk files. Typically, a chunk file is by default 1 megabyte. And then the second information that the metadata service will tell you is where you have to store them. And then you can directly contact the storage services, so that's different servers, and they will store the files, the chunk files at the right position. It's important to keep in mind that one storage service may have access to different so-called data storage that can be seen as kind of partition. You will see it will be important for data mirroring. Another very interesting thing is that so both metadata and data servers never access directly the disks. So they build everything on top of classical Linux POSIX file systems, such as ext4, XFS, ZFS. So you have some freedom there to optimize according to your needs. OK, let me discuss a little bit the data and metadata mirroring. So you can create in BeeGFS what is called buddy groups, which are groups of targets of metadata or data. And this is illustrated here in this slide. So imagine you have 4 data servers. They have access each to only one storage target. You see that you can, for example, group target number 1 with target number 2, and target 3 with target 4. And in case, of course, of strong failure of one of the servers, you keep the integrity of the data. So this works also if you have only 3 data servers. In this case, you need to have at least 2 targets for each storage server. And you see that by creating different buddy groups, you can be safe. So you can lose server number 3, and your data will still keep the integrity. Unfortunately, so this is it's mirroring, so it corresponds to a RAID 1 approach. So, I mean, if you want to mirror everything, you lose a factor of 2 in the storage, in the total storage. However, there is something which is interesting. You can precisely fine-tune the file system at the directory level. So you can say, OK, this directory and everything that goes inside will be mirrored, or another won't be. So you can really decide at a very low level what will be mirrored or not. So you can save storage capacity with this approach. OK, let me now go into some details on the hardware we installed to create our BeeGFS file system. So, in Geneva, we built it based on 2 metadata servers, and we added first 2 other data servers, and finally we extended it with 2 other ones. So in total, we have 4 data servers, and everything is interconnected with an InfiniBand system with a rate of 40 gigabytes per second. OK, now this gives us a total capacity of 800 terabytes without counting files that are mirrored. So in more detail, so our 2 metadata servers are TransTech machines. They have each 2 CPUs, 16 core with a CPU frequency up to 2.1 gigahertz. RAM is 64 gigabytes. And each of these metadata servers have access to 4 disks, so 4 SSD disks, because we really need speed here, in a RAID 5 array. And so this gives a partition dedicated to the storage of the metadata of a size of 2.7 terabytes. The first group of metadata servers are composed of, that's again, TransTech machines. They have access to 24 disks, so they also have 2 CPU, 16 cores with a slightly lower frequency, and RAM is something like 128 gigabytes. So with these 24 disks, so having each 2.7 terabyte of capacity, so we created 2 partitions, RAID 6, so 10 disks plus 2, and we have a final capacity of 2 times 72 terabytes. And finally, the 2 last data servers, they are a bit different. So the server itself is a Dell machine, which is connected to 2 GBUD. So we have in total 48 disks. The first GBUD is filled with 5.5 teraoctet disks, the second one with 7.2. And we created here 4 different partitions. So each of them, in each of them, the disks are in RAID 6 arrays. And so we have 2 times 55 terabytes of storage and 2 times 72. So in total, this gives us about 800 terabytes. OK. Some information about data redundancy. So this is a very simple sketch of our system. You see the 2 metadata servers and the 4 data servers. As I told you, all disks are in RAID arrays. So RAID 5 for the metadata, RAID 6 for the data. So in case we lose some disks, there is no problem. I mean, the storage system is absolutely not affected. Then if we lose completely one data server, for example, if there is a crash in the main board, as long as the data won't be affected, I mean, we simply have to reinstall it. The integrity will be completely conserved. All those data are in a buddy mirror. So as everything is symmetric, it's quite easy to decide for this buddy mirror. So each data target has its equivalent on the other data server. And then with this setup, we can completely lose one of the 2 metadata servers, and you can still work on the system. So the storage system is not affected. Now, if unfortunately you lose a data server here, so by really losing, it means that everything exploded or disappeared. So you not only break the system, but also the data. So I don't know exactly how this could happen. Anyway, in this case, you will lose all the data that are not mirrored. So if you mirror, of course, everything will be conserved. OK, let me now finish by showing you quickly some benchmark we recently performed. So the setup for this benchmark is the following. So the chunk, each file so the chunk file size is fixed, with a size of 1 megabyte. And the number of targets, of storage target for each file is 12. So we use all the target for every file. Okay, the first benchmark we run is very simple stuff. Is a little Python script that simply writes a file, but we change the size of the file starting from 32 K up to 16 gigabyte. And the idea was to compare the writing rate of our BeeGFS system in blue here with two other file systems we had. One which is based on a RAID 6 array of HDD, and the other on 8 SDD disk in RAID 0. And you see that, of course, if you run this benchmark, this simple benchmark on HDD or SDC, I mean, the writing rate is nearly constant. However, if you use your BeeGFS, you see that for very small files, of course, you have an overhead because you have to contact first the metadata server before writing the data. But you see that very quickly this curve increases, and you see that you are much better than the two other file systems for file size of about 10 megabytes. The second benchmark we run is a benchmark called IOBench, which has been written by one of our colleagues in the CSCS team at EPFL. So it's a C code where there you run n tasks in parallel, and in the first approach, each task writes its own file in the file system with a size of 512 megabytes. And here you see the writing and reading rates as a function of the number of written or reading files in parallel. And so you see that you reach for 192 tasks that write in parallel, you reach a rate which is up to 8 gigabytes per second, which is quite nice. And we did, we'll skip that, but we did the same test, but now forcing all the tasks to write in a single file, which is quite different, so using MPI-IO approach. And here you see that the performance is not so bad. I mean, you see that curiously, both writing and reading rates are nearly similar and grow up to 6 gigabytes when you use nearly 200 tasks. Okay. So that's just to tell you that, in fact, if you change, for example, the number of storage targets per file, so if you force one file to be written on only storage partition, I mean, you drop in performance, of course, because you don't benefit of the full file system. So let me now conclude. So we are definitely globally satisfied by these new HPC storage systems. We find it very easy to install, to deploy, to maintain, and to extend. I mean, this is also very important. And the performance are enough for our users, so they're good. I think in the future, BeeGFS could be slightly improved. One main drawback is the fact that when you mirror data, I mean, you have only a kind of red one. You can only mirror using a red one, so you lose half of the storage, which is really bad. So I hope they will think about implementing at least a red 5 grid. And finally, I didn't discuss at all this point, but so quota exists on these file systems. You have user and group quota, but they are very simple, and some improvement could be expected at this level. That's it. Thanks.
Any question? I want to pick up the previous. When I mentioned BeeGFS, you, Diego, said something about metadata not totally reliable, but you feel satisfied and safe enough.
Yeah, sure. But I think it's because the requirement of our user are not so strong. I mean, we didn't really, the only trouble I can see here is that if you, of course, switch off the two metadata servers at the same time, and someone is writing a very big file. And so in this case, I don't know exactly what will happen. But anyway, this is something, well, in your case, this will, for example, break down the simulation that was running, and you will simply ask the user to read. So that's definitely an issue. So we are in a, and well, as I was saying, I mean, the requirements of our user are not so. So it's why we can rely on this BeeGFS file system.
Okay, but using two servers at the same time is kind of unlikely. So I think
Who knows?
the system is relatively safe, I would say. At least for us, it's very good.
BeeGFS, you can multiply the number of metadata servers. In our system, we have two metadata servers which are replicated on two replicas. So this way, you can ensure that your metadata are safe.
But even if you, I mean, imagine that you have everything break down due to a power failure, for example. So in this case, you cannot guarantee that everything is, well, all what has been written before the failure will be fine, but what is written during the failure could be corrected, no?
You can't ensure that in any system.
I agree. So what I want to say is that shit happens, and these failures can happen at some time. It's a network cable,
Sure.
Electrical failure. So the thing that you want to ensure in the client is to give the error that the data has not been saved. So the user receives an error. No, your data is not here. You get an error, so that he will try back. The worst that can happen is you say, okay, but then, because imagine you have, first you interact, and then the persistence is done asynchronously. So imagine the failure happened at the time you acknowledge the user that the file is okay, the metadata is restored, but you are still in the process of syncing the disk or ensuring the persistency, so the user get the okay, but it is not okay. So this is really what you want to ensure, that when it is there, the user knows.
Yeah.
Sorry, Diego wants to say something.
Yeah, first of all, to clarify this concern I have, it is on journaling, actually, because BeeGFS is, well, I've been always told that it is not a journal file system, so atomic operations are not that safe in case of power going down. But that said, I agree that GPFS, in terms of management, it is extremely easy. And I was thinking, actually, and I want to, this is the question I have, what do you think about a BeeGFS used as a file system that is deployed on premises in a batch scheduler? Some people are starting to deploy file systems. So BeeGFS
has this ability. Indeed.
How do you think? How easy do you think it could be to integrate in a scheduler a BeeGFS allocator for new file systems?
So I have no experience with that, but there is what is called the BeeGFS on demand. So you can, as soon as you schedule a job, create a temporary file system. I didn't check how it works, but this is a new feature in the last release of BeeGFS.
I have tested it on a 20-node computer on SSDs, and I was disappointed because I got only 10,000 IOPS. But it's because I had only 10 gigabit network. So maybe with InfiniBand it might be better. But I was quite disappointed with the performance, the IOPS performance.
Okay, we thank you. We have to move on. You have a question. Sorry.
For the mirroring, you need a license. Is that true?
That's right. I didn't discuss this point. So both for the quota and buddy mirroring. That's right. So it's not completely free.